begin. Thank you. Hi everyone, welcome to this summer school. And as you probably know, the polynomial method existed since the 1900s, when people used it for understanding solutions to the Diophantine equations. In the 80s, it was used in computer science, but it was only introduced in incidence geometry in 2008 by Dvir, a computer scientist, to solve the Kakeya problem in finite fields. So this method really revolutionized incidence geometry and later harmonic analysis because it showed us that there is underlying algebraic nature in some big long-standing problems in the fields that we didn't know about. And here I'd just like to talk about the first time this method was used by Dvir. First, some notation. This is about comparison in terms of order of magnitude. So if you have quantities A and B inside, these are real numbers, but let's say they are the sizes of sets, for example, in f to the n. We say that A is bigger than B with one wiggle if A is at least a constant times B, where the constant only depends on the dimension. So A could be smaller than B, could be like 1 over n times B. That's still okay. And if B is larger than A in this sense, then the second notation holds, and they are comparable if both the above. Okay. So for example, if we say we have a bunch of L lines and we want to look at their pairwise intersections, for example, this could be even about L choose the pairs of lines, and that is comparable to L squared in this sense. And the idea is that just every constant is just 1. Now with two wiggles below, let's say we have quantities A and B that depend also on a parameter delta that can be as small as it wants. Then A is bigger than B in this sense with two wiggles, if A is allowed to even be quite smaller than before. So it can be at least, or it can be even as small as 1 over log of 1 over delta to a power that only depends on the dimension times B. And we allow a constant at the front that again only depends on the dimension. And of course, this second thing means the reverse, that B is bigger. And both the above mean that the two quantities are comparable in this sense of two wiggles. And the idea here is that 1 over log of 1 over delta to powers is just 1. Okay. So we're going to be using this stuff. First, I'd like to talk about the actual Kakeya problem in Rn, and then create a discrete analog that Dvir eventually solved. Please interrupt me at any moment if you have questions. So a Kakeya set in Rn is a compact set that contains a unit line segment, a line segment of length 1, in every possible direction. So this means that no matter what direction you choose here in the unit sphere, inside your Kakeya set K, you will be able to find a copy of that direction somewhere. Same if you take this direction, a copy will exist somewhere in the Kakeya set. Same for this direction, and so on. And since a Kakeya set contains a unit line segment, so something of positive length, in every one of these directions, which are many directions, we expect that they should be large Kakeya sets in some sense. But there exist Kakeya sets of measure 0. It is conjectured, though, still that they are large in the sense of Hausdorff dimension. So the conjecture is that every Kakeya set in Rn has Hausdorff dimension, that I denote by this, as big as possible, as large as the ambient dimension. And this is only known in 2 dimensions, and even the weaker version for the upper Minkowski dimension, that is still not known. So the fact that the Minkowski dimension of a Kakeya set is full, this is still not known. It would be implied by the Hausdorff dimension estimate, but we don't know that. So this Minkowski dimensional conjecture is the one that will lead us to the discrete formulation that Dvir solved. So let's discuss it a bit more. Let's say that we want to show it. So what is the goal? We want to take any delta neighborhood over a Kakeya set. We denote it by K delta. So that's every delta thickening of the set. And we want to show that this is big in Lebesgue measure. It has big volume. So if we wanted to show that the Minkowski dimension is alpha, we'd be aiming to show that every delta neighborhood is at least, and here allow log losses, delta to the n minus alpha. Now that I want dimension n, this means that the exponent will be 0, and this is what I'm hoping for, that the delta neighborhood of every Kakeya set is big. So even though Kakeya set can have Lebesgue measure 0, as soon as you slightly thicken it, it will have very big volume. And let's just try to understand the delta neighborhood of the set a bit better. So here is K, I look at K delta. Every line segment of length 1 that the set contains will be turned into a delta cube, as we call it. So a cube of cross-section delta and radius and width, sorry, in length 1. So this will be delta in radius, and the length will be 1. All of these are called delta cubes. They all have the same size, the same dimensions. Okay, and of course, since the Kakeya set contains a unit line segment in every direction, this neighborhood here contains a delta cube in each direction. Okay, and I want to use this information that for every direction have a sort of fat object, a delta cube pointing there, to show that the union of these delta cubes is quite big. Now, not all directions are going to help me here, because imagine this situation. I have this, and there could be in the Kakeya set, or its thickening, another delta cube that's extremely close to that, but in a different direction. So it could be, say, pointing to a slightly the direction of the original one, slightly different. I still have two cubes here pointing in different directions, but they look like there's still one cube. So the existence of these two directions won't help me at all. But as soon as the angle between two cubes starts becoming bigger, so in fact more than delta, the cross-section width, then I start seeing them as different cubes. So the useful thing for me is that K delta contains a maximal family of delta separated delta cubes. By delta separated, I mean that the angle between any two of them is at least delta, the cross-section width. And this information should be able to help me to show that the union of these specific cubes is big, because they actually point in different directions. And to find the delta at separated directions, here, I'm just going to take a cover of the sphere by delta caps, finitely overlapping delta caps. And for every one of them, I get at center, it's a different direction. So this is how many cubes I expect will be useful to me. As many as the delta separated directions. Okay, so now this fact gives me an equivalent formulation of the conjecture that I will write here. It says that for every delta positive, for every maximal family of delta separated cubes, delta separated delta cubes, in Rn, I have that their union must be big. The union of the cubes in this family is at least 1, whatever that means. And I want to understand this a little better. So I want to understand what this 1 actually means on the right-hand side. So the question is, how does this quantity, relate to the cubes they have, the family of cubes that they have? Okay. And here we can notice two things. We need to understand numerologically our problem a little better. So one, how many cubes do we have? What is the size of the family of cubes? Okay. So there are as many as the delta separated directions. So here is a sphere. Let's pretend that there is a sphere. And let's just cover it by finitely overlapping delta caps. Okay. So the number of these caps is the size of our family. So this is comparable to the size, the size of the surface area of the sphere over the surface area of every cap, which is about 1 over delta to the n minus 1. Okay, that's how many cubes we have. And now every cube has the same size. Let's calculate that size. So for every cube in our family, the size of the cube is its cross section times the length. So the cubes are have a cross section that's an n minus 1 dimensional ball of width delta. So the cross section has this size and the length is 1. So it's about delta to the n minus 1, the size of every cube. So 1 is the product of these things, which means that 1 is the number of cubes times the size of each. In other words, it's the sum of the sizes of the cubes. Okay. And that is a much nicer way to understand this right inside here. That's what the conjecture says. It says that if you unite all your cubes together, that union is bigger, in some sense, than the sum of the sizes of the cubes. Now the reverse direction, this direction, is always true. If you unite two sets, the union can't be bigger than the sum of the sizes. So we actually are aiming for comparability. We want to show that these two quantities are comparable up to log losses. In other words, we want to show that the cubes behave as if they are disjoint in some sense. So if the cubes were actually disjoint, then their union would have exactly this size. That would be the largest possible size the union could have. We want to show that even though they overlap, then the union still is pretty much that big. So we want to, that is how I remember the Kakeya problem. It says that in some sense, cubes pointing in different directions and by different, that different depends on their width, behave as if they are disjoint. Okay. So together they will cover up a lot of space, as much pretty much as if they were disjoint. And this, and morally, would mean also that their overlap is very small. So the cubes can meet, of course, they can pile up on top of each other, but that shouldn't be happening on large areas. In principle, they should spread afar so that they create a lot of mass together. So this is a way we can remember what the conjecture says. Okay. Now this problem is very difficult. It's only solved in 2 dimensions. And the problem about it is that cubes are thick. So when you have 2 cubes, their overlap depends on their angle of intersection. The smaller angle between them they have, the more they intersect. And that makes things difficult in higher dimensions. So we would like to simplify the problem and get a discrete analog where every cube has been shrunk down to a line. and every delta cube in it is shrunk down to a point. We want a setting like that, and that could be useful because maybe the volume, even though important, is sort of foggy in our view to structure that exists. So if you remove the volume, you get a simpler problem, yes, but maybe it's going to be useful. And the question is, in what universe shall we consider this problem, where every cube is a line and every cube is a point? And something to notice is that every delta cube consists of finite, well, it can be fully covered by finitely many delta cubes, disjoint. So we want a universe where every line consists of finitely many points. So here we want about 1 over delta points on this line and no more points. And the correct universe in that sense to work in is f to the n, where the size of the field plays the role of 1 over delta. This is a world where every line contains exactly this many points. The line is a copy of the field. And the original Kakeya conjecture says that if you take, in the continuous world, a cube in every possible direction, well, in every possible one of the delta discretized directions, then their union will be big. We want to conjecture the same in finite fields. So if you take a line now, in every one of the possible different directions in f to the n, then their union should be big. And I'd like to draw your attention to the numerology that fits quite well, not surprisingly, that the delta separated directions, the number of cubes in the continuous world, agrees with a number of different directions in finite fields. This is a hyperplane worth of directions. That's how many you know. Okay, so let's just remember the Kakeya conjecture on the left and create it on the right. So on the left, we want to show that the union of these cubes is at least the sum of the sizes, or pretty much anyway, the sum of the sizes of the cubes. And this is exactly what we'll ask in the discrete world. We want to show that the union of lines, when they point in different directions, is at least the sum of their sizes. And here I don't put a double wiggle, I just expect a constant loss. Because actually the logarithmic losses for cubes usually come from the fact that the cubes have thickness. Here, and remember, the logarithm depends on the thickness as well. Lines don't have thickness, we shouldn't have any losses. Okay, so to understand the right-hand side in discrete setting a bit better, we write this out. This is a number of lines times the number of points on every line. On every line, we have as many points as the size of the field. So this is times the size of the field. How many lines do we have? We have one in each direction. So it's as many as the different directions. Is there a question?
We just have a lot of people joining, so I'll mute them as they come in.
The number of directions is f to the n minus 1 times the size of the field, so I'm getting about f to the n. And that's the conjecture in finite fields. It asks the same thing as in the continuous world. So to understand it, to feel what it says that if lines, you have one line in each direction, then together they should cover up pretty much the whole space up to constants. That's the ambient space f to the n, that its size. So the union of the lines should be at least 1%, at least 1% of the ambient space, but no less. Okay. And that is what Dvir proved. So he said, let's take a Kakeya set in f to the n, where f is a finite field. And by Kakeya set, we mean exactly this. A set that contains a line now, a full line, a copy of the field in every direction. Then the Kakeya set should be at least proportional to, in size, to the whole ambient space. And by line, What do we mean? The line passing through a point A in direction B, where A and B are in F to the n, is defined as the set of A plus T times B over all T in the field. So that is indeed a copy of the field. And the direction of this line is B, or any multiple of B anyway. Right, so let's, so Dvir showed this using the polynomial method. So let's just see some very basic ideas behind the polynomial method. That's a general plan, not even the method he used yet. So here is the idea, an idea, to count points inside the set S that live on lines inside the set L in F to the n. And here F is any field, it doesn't have to be finite. So the first step is to find the low degree polynomial that vanishes at the points we want to count. So everything red for me is in the zero set of that polynomial. So I'm trying to find the polynomial that makes all my points red. All the points should live in the zero set. I can imagine the zero set as a surface in Rn, for example, passing through all of these points. So here is ZP, the zero set. And now we want to check in step 2 how this vanishing property, how this redness propagates across the lines in our family. Because polynomials have this property that they infect lines. If something happens for a polynomial a lot across a line, then it happens throughout the whole line. That's some general kind of rule or moral. And I'll return to this picture, but the most basic lemma here that actually goes a long way is that if a polynomial in n variables my pen is starting to fall apart. These things always happen at the wrong times. So if a polynomial in n variables vanishes on a line L more times than its degree, then it vanishes along the whole line. Then the line is contained in the zero set itself. So that ZP is the zero set of the polynomial. And in fact, we have something better, better for finite fields, that P restricted along the line when seen as the polynomial of one variable is identical, is the zero polynomial. So by this, if the line is AB, the line passing through a point A in direction B, the restriction, I define it here, let's say to be the polynomial, original polynomial, applied only at the points of the line. It's a polynomial in one variable. And this is the zero element. Okay. So why is this true? Let's see, let's take our line, here it is. And let's say here we have the points where the original polynomial vanishes, that's where P vanishes. Well, this can be parameterized by elements of the sort. You can find all these different T's where this new polynomial vanishes. So you have that P restricted on L, this polynomial in one variable. It's a polynomial of one variable that has more than its degree roots. So it has more than the degree of the polynomial, original polynomial roots, and that's at least the degree of our one variable polynomial. And the polynomial cannot vanish more times than its degree unless it is the zero polynomial itself. So we'll take a break and we'll try to change okay. I'll turn off my camera for a moment, okay? Because I'll freak out.
Sure.
Okay, so here is the moment of truth. It's working, yay! Okay,
Wonderful.
so this arrived yesterday or 2 days ago.
Great.
Sorry for the delay. So we have a polynomial of one variable, vanishing more times than its degree, so it must be the zero polynomial. And that is stronger in finite fields. It means that all of its coefficients are zero. Okay, so let's go back here, see what this vanishing property means in the picture. So it means that we have a dichotomy. It means that for every line in our family, either the points in the line, so the polynomial is vanishing on our points, remember, right? That's how we chose the polynomial. Either these roots along the line are fewer than the degree, are at most the degree of the polynomial, or they are more, which means that the line is fully in the zero set, or even better, that the polynomial restricted there is zero. So here you have a lot of lines here, the ones that contain more than the degree points, that are completely engulfed by the zero set. So they are also painted red. So for many of the lines, this will happen. And for the rest of the lines where this doesn't happen, so like this one, let's say it doesn't lie in the zero set, or this, we know that those will contain very few points. We'll have control on those lines. So these black lines contain at most the degree of p points of S. That's control. That gives control on S. When you want to count the points in S, it's a very good estimate to know. And for the other lines that are in the zero set, we have structure. Because they are in the zero set. So this is a very nice dichotomy that helps with counting. The black lines you can ignore because you know how many points you have on each at most. If you chose a small degree, then this is a very good bound. And then you have reduced to a problem where you can ignore completely these black lines. Everything is just what's left. Anyway, you can ignore the black lines. So all that remains is points and lines that are red, meaning points and lines on the zero set. So you started with a difficult problem where you knew nothing mainly about points and lines, and you reduced the situation where everything clusters on a zero set of low degree. And that gives a lot of structure that you didn't have before. Something, for example, you can check, you can use is whether the gradient of the polynomial is zero or not at any point. That is telling you whether a tangent space exists or not, for example. And you can study more of that stuff of that sort. So that's why the polynomial method helps to count points and lines. Partly why it helps. And so I'd like now to say what Dvir's vanishing lemma was, the lemma that he used, the polynomial method that he used. But before that, I'd like to emphasize what it means for a polynomial to be zero, because that's important. A polynomial in n variables is zero if all of its coefficients are zero. And that is different to saying that the polynomial vanishes at every point in f to the n. In Rn, it's the same. A polynomial is the zero polynomial if and only if it vanishes everywhere. But in finite fields, it's not the same. For example, you can take the polynomial x to the p minus x in zp of x, so one variable polynomial. This vanishes everywhere on zp, but it's not zero. It's not the zero polynomial because its coefficients are not zero. Okay, so it is important to remember this. And now what Dvir showed is that if you take any n points inside f to the n, where f is any field, it doesn't have to be finite. So the number of points matters here only, how many they are, but not where they live exactly. No structure about them is related to this. So let's take n points in f to the n. Then we can actually find a low degree polynomial whose zero set passes through all of these points. And what I mean by low degree, the degree depends on the number of points, but it's actually even smaller than that. So degree at most constant times the number of points to the 1 over n. No matter what n points you have, you can find the polynomial that vanishes at those points, and it has this small degree that only depends on the dimension and the number of points. This is what he used to prove that Kakeya sets are big. He took a polynomial of this degree vanishing on the points of the Kakeya set, and he saw what kind of structure that means for the picture, like we said earlier. Let's prove this lemma because it's easy. So you you have n points. Let's call them y1, y2, up to yn. These are the n points. And we want to construct a polynomial of low degree that vanishes at those points. So we're looking for a degree, first of all, and for coefficients such that this happens. So we're looking for non-zero polynomial in n variables. And of course, this will look like a sum of coefficients of monomials. So these are coefficients that depend on the exponents of the monomial. Here is the monomial, and the exponents should be adding up to at most d. Okay, we're looking for such a polynomial that's non-zero, such that it vanishes at all the points, such that p of y1 is 0, p of y2 is 0, etc., all the way up to the nth point. Okay. So really what we're looking for are the coefficients here. And for the polynomial to be non-zero, we just need one of the coefficients to be non-zero. In other words, we're looking for coefficients not all zero, such that these m equations are satisfied. Okay. So let's study one of these equations. This means that if you go and plug in here, in the place of the xi, the coordinates of this first point, explicit coordinates, you're gonna get 0. And this is actually just a linear equation with these unknowns, the coefficients. So our equations are m linear equations. And the unknowns are the coefficients, and we know how many they are. They are as many as the n tuples that satisfy this. And this is d plus n choose n. Or just for simplicity, it's about d to the n unknowns. So we have a system of linear equations with a specific number of unknowns, and we just want to show that there exists a non-trivial solution. We want to find for what d, for what degree, there exists a non-trivial solution. So we are okay, there exists a non-trivial solution if the number of unknowns is bigger than the number of equations. And this means that d to the n, the pretty much number of unknowns, is at least the number of equations, or equivalently, d is at least n to the 1 over n. So what does this mean? It means that there is this threshold, which is about m to the 1 over n, and for any number d we choose that's above that threshold, for any number d we choose bigger than that, we are okay. So we'll just pick the lowest d we can, that's here, about n to the 1 over n. So we're okay, even if we choose d to be about that threshold. And what does this mean? It means that for this d, which is about this big, there exists a polynomial of degree at most that d, and therefore at most m to the 1 over n, satisfying exactly what we want. So this was just parameter counting and had nothing to do with the structure of the points in space, which makes it in some sense very powerful because it holds always, but also weak because it doesn't take into account the structure. In any case, it was good enough for the Kakeya problem. And here is the solution. First, let's just do a sketch. We'll suppose that our Kakeya set is small, smaller than a proportion of the field, of the ambient space, and we'll get a contradiction. So here is a Kakeya set, and because it is small, we'll use the vanishing lemma, which is described, to find a very low degree polynomial that vanishes on k. So remember, the degree of the polynomial depended on the size of the set only. So if the set is very small, your degree will also be very small. So we'll find a very low degree polynomial vanishing on all of our lines. And from this, we'll take another polynomial that vanishes on all the translations through 0. So we'll floor all of our lines through 0. The point is that these are a point in all possible directions. So when you translate them to pass through 0, you create all lines through 0. In other words, you create a whole space. So you get another polynomial of low degree, same as the original actually, that vanishes everywhere. And that we know, for example, can't happen in one dimension. A polynomial of one variable cannot vanish more times than its degree, for example. And in general, we will get a contradiction as well for the general case in n dimensions. Low degree and vanishing everywhere are not compatible. And that's where the contradiction comes from, to the original assumption that k was small. And now let's just do the actual proof. So we suppose that the Kakeya set is smaller than a small proportion of the field, the ambient space, where this Cn is a small constant, think of it as tiny, that will be determined very soon. So the first step, remember, was to find a low degree polynomial that vanishes on our set. We know by the vanishing lemma that there exists non-zero polynomial in n variables of degree at most a constant times the size of k to the 1 over n, vanishing on k, on the Kakeya set. Okay, so the information so far is that all these points are red, they live in the 0 set. That's what we have. And I'd like to study the degree a bit better. We said it's a small degree. How small is it actually compared to the field we live in? Okay, so precisely, there is a constant hiding here. Let's call it an. The degree is at most a specific constant that comes from the vanishing lemma, has nothing to do with the problem, times the size of k to the 1 over n. And we assume that the Kakeya set is small, so this would be smaller, the degree would be smaller than an times cn to the 1 over n, the unspecified constant here, times the size of the Kakeya set. Sorry, the size of the field. Here we go. And now we will choose our little constant cn here, so that this is smaller than 1. And therefore, so that the degree becomes smaller than the size of the field. And okay, all you need to do is to pick cn smaller than an to the minus n. Any number in that threshold, in that below that number will be fine. And the interesting thing here is that the degree we picked is smaller than the size of the field, and the size of the field, we remember, is the length of every line. In this universe. That's how many points the line contains. Okay. So for the second thing, we need to see how this vanishing property propagates to all of the lines. And here is where you use, so let's look at the line. Here it is. Oh, okay. We have that the polynomial vanishes at all of these points along the line. Okay, so let L be inside the Kakeya set. It's a full line, a copy of the field inside the Kakeya set. And we know that the polynomial vanishes at all of its points. So P vanishes on all the points of the line. So it means that it vanishes more times than its degree, right? The points on the line were more than the degree. We just explained that. So P vanishes on L more than its degree times. And as we said earlier, this must mean that restricted on the line as a one variable polynomial, it will be 0. So P restricted on the line is the 0 polynomial in this universe of polynomials of one variable. So all its coefficients are 0. And this is slightly stronger than saying that it vanishes, as we said, at the points of the line. So here is a slightly stronger vanishing property. Oops, sorry. Slightly stronger vanishing property that we have. I will draw the line red, and we'll think that this means that P restricted on this line is the 0 polynomial. Okay, so I have this thing for all the lines here in this picture. And now, let's just see what this means. If a polynomial restricted along the line, along a line, is the 0 polynomial of one variable, what does this mean? Well, Dvir show that it means that some other polynomial will vanish on the direction of the line. This polynomial, I should emphasize, is in n variables, like the original polynomial, like P. And it actually comes from P. It is the homogeneous part of P of highest degree. So HP is the homogeneous part of P of highest degree. You get the highest degree monomials of P, you add them together, and that is HP. So it's part of P. And it's homogeneous, actually. So this means that it doesn't just vanish on this vector, it vanishes at all its multiples as well. So it must vanish along this whole line through 0. So HP vanishes along, at all points, I mean, the translation of L through 0. Okay. And something, of course, to notice is that it has the same degree, this polynomial, as the one we started from. So the degree of HP is just the degree of P, because it was just the highest degree monomials together. Okay, so we start with a polynomial in n variables, that's P, that vanishes on the lines of our Kakeya set. If we take any single line and we restrict the polynomial there, we know that the polynomial is 0. That's information that's one-dimensional. So we take this information and convert it back to n-dimensional information, but for a simpler polynomial. Okay, if the polynomial vanishes along a line strongly, then its homogeneous part will vanish on the line through 0. let's just see the proof of this little piece here. It's very simple. We know that this polynomial, in other words, the polynomial of one variable, restricted on the line, is the zero element of this space of polynomials, which means that all coefficients are zero. I want to use the stronger information that's simply vanishing at the points of the line. I just need to understand the coefficients, and in fact, this homogeneous part applied on the direction will be one of the coefficients. So if the original polynomial is the sum of these monomials, multi-indices, so m is a multi-index here, adding to at most the degree of p. Then to get this polynomial of one variable that I know is zero, I just need to replace a plus tb in x. And when you do the, so this is a power here, you raise things to that power, there are many brackets, you multiply things out, and you notice that you'll get t to the degree of p, that's the largest degree monomial. Its coefficient will come from operations only on this b. So it will actually be the homogeneous part of highest degree applied to b, plus lower degree terms. Okay, so this is a coefficient, and it's zero, and that's it. So that is what we proved, what Dvir proved, that if a polynomial vanishes strongly along a line, then its homogeneous part vanishes along its translation through zero. And now we apply this for the Kakeya set. We have seen that this polynomial we started from vanishes strongly at all the lines of the Kakeya set. So the homogeneous part will vanish at all the translations through zero, but the Kakeya set contains lines in all possible directions. So when you translate them to pass through zero, you create all possible lines through zero. And therefore, this homogeneous part of highest degree vanishes everywhere on f to the n. And that is how you get some, this is how you get a game. So you had all these directions here, but there was overlap. Through this idea, you sort of look at every line independently. They all become disjoint, pretty much. And the question is if this even makes sense. This is a low degree polynomial. Its the degree is the same as the degree of the polynomial we start from. It was at most the length of every line, smaller than that. And the question is, can it vanish everywhere? So let's think. If n was 1, if we worked in one dimension, would this be possible? We'd have that HP is non-zero, of course. It's homogeneous part of highest degree, so it's non-zero. And has degree equal to the degree of the original polynomial, so smaller than the size of the field to the 1. So it cannot possibly vanish on the whole of f. So can't vanish on here. The polynomial of one variable cannot have more roots than its degree. And actually this generalizes to all dimensions through a lemma that's called the Schwarz-Zipf lemma. So it says, let's take a non-zero polynomial in n variables now, not just one. Then its zero set, just points now. This is an infinite field set only. These are just points in the f to the n. Its roots cannot be more than this quantity. I won't prove it. It's proved by induction from the case n equals 1, actually. But I'd just like to say that for n equals 1, it just says that the number of roots of a one variable polynomial is at most its degree, as long as the polynomial is non-zero. And I'd like to explain how to remember this. It says that that the zero set is largest when it's the union of degree of G many parallel hyperplanes. So here is a worst case scenario where the zero set is here. Each of these is a hyperplane inside f to the n. So the size is f to the n minus 1. And how many do I get? The degree many of these hyperplanes. This is exactly when I'd get equality here. Well, at least one case where I would get equality. And this would be the case where G of the n variables would be, say, a product of n linear terms, xn minus a height times xn minus another height times xn minus a final height. Okay. So I'm just saying this because there are continuous versions of this lemma called the Wonki's theorem, and you might remember it more easily if you see it through this. Okay, so just to finish the proof of the Kakeya conjecture in finite fields, we had that HP vanishes. So before, we were led to saying that this polynomial vanishes everywhere on f to the n, on all points of f to the n. But we know that its zero set, just from the start simple lemma, cannot be too big. It's at most its degree times the size of any hyperplane. And this is equal to the degree of P. It was smaller than the size of the field. So this will be strictly smaller than the whole ambient space. So we get a contradiction here, and that's it. The Kakeya set must have been small. So notice where we use the smallness of the Kakeya set. We used it, okay, we used it, for example, here. That is necessary. The Kakeya set, if it's a very small proportion of the ambient space, that polynomial you find is of very small degree, and you need it with a small here to get some contradiction. And we also use the smallness of the Kakeya set to get the strong vanishing along every line. So vanishing on the points of the line meant that we have identically zero polynomial on the line. Okay, so this is what I wanted to say today. Maybe we can stop the recording and go to questions.